Hello, this is Dr. Pratima, Faculty in Physics, Institute of Aeronautical Engineering, Hyderabad. So in my present lecture, let us discuss about the extrinsic semiconductors, which is an extension of my previous lecture, where we have calculated the number of electrons and the number of holes in the conduction band and the valence band respectively in intrinsic semiconductors after seeing the types of semiconductors and how the semiconductors are falling into the classification of materials through the origin of the band gap formation. So if you want to see all these topics, you can go into my previous video lectures. So now let's have a start of deriving an expression for the n-type semiconductors, where first we will see what are the extrinsic semiconductors. Let me just give an outline of this talk. In this video lecture, you will be knowing what are extrinsic semiconductors and how are they falling into different types and what is an n-type semiconductor, which is our present topic. And we will be seeing the carrier concentration in the n-type semiconductor. And we'll also see how the Fermi level will vary with temperature and the donor impurities. First, this is a revision slide of my previous lecture for the people who are just watching this video, my videos for the first time without watching the previous videos. This is just to help them. So the classification of the semiconductor is given, where the left side is not in our curriculum, the right side is in our curriculum, which the semiconductors are classified based on the impurities. If there is an impurity, then it is known as extrinsic semiconductor. Else, if you are taking any pure semiconductors, it falls as an intrinsic semiconductor. So as of now, we are looking into the intrinsic semiconductor, where the present topic is n-type. So now, why is an extrinsic semiconductor, why should it exist apart of the intrinsic semiconductors? As I have told you in my previous videos, intrinsic semiconductors, though they have good physical properties like hardness and the good covalent bonding along good direction between the neighborhood atoms, they will not be having good conductivity. So, because there are no free electrons. So now, in order to raise the conductivity, we will have to modify the intrinsic semiconductor. So how can you modify? You will have to add some other compound or some other elements to it. If you take the periodic table, there are almost 11 semiconductors, and germanium and silicon and many others, or a few of the semiconductors, of which germanium and silicon, we have already taken them into consideration in intrinsic semiconductors. So if you can dope them with the third and fifth group atoms, then you can observe a rise in the conductivity and many other properties of the intrinsic semiconductor. This process in which you add the other elements into the intrinsic semiconductor is nothing but you are taking the adding as an impurity, because just you are disturbing the purity, but it doesn't mean that it is something like a dirt. Okay, so the process really is very hectic. It needs high temperatures. For suppose you are adding gallium arsenide or you are depositing it onto a substrate, you will have to allow it to pass. If you are adding some sulfide, you will have to allow it through a gas chamber in vacuum, where the temperatures will be very high to large amount of time, around 600 Kelvin even. So this process is known as doping, where you add something into or some other elements of either third group or fourth group, which fall third group in the sense which fall into the 13th and 15th row, like column elements. Okay, so as of now, let us take the fifth group atoms to consideration. So what will happen if I add this? Okay, so before going into that, whatever the process you are doing is doping, and the element which is being added taken as an impurity is known as a dopant. So if you are taking a fifth group element, like it will be having pentavalency, in the sense 5 valence electrons in it, that is 5 electrons in the valence shell when you take the electronic configuration. For example, if you take phosphorus, it is having 5 valence electrons, and let us see how these electrons will be shared when you are taking it into the lattice of a pure semiconductor, which is an intrinsic semiconductor. So what will happen is, this 5 valence, out of the 5 valence electrons, 4 valence electrons will be sharing the covalently bonded covalent bonds with the neighboring atoms, whereas 1 is left free, which is known as the free electrons. Thus, the free electrons are generated when you add a pentavalent impurity to an intrinsic semiconductor. Or in other case, I can also say that the impurity or the dopant which you are adding is donating its 1 electron to the lattice, which is the mother lattice, that is the silicon or germanium if you take. Okay, so if and this will form an energy level which is known as a donor energy level. We will see how this will happen through this picture. So this phosphorus, which is having 5 valence electron, which you can take it as like this, 1, 2, 3, 4, and this is the fifth one. The fifth one is 1, 2, 3, and 4 are covalently bonded with the neighboring silica atoms, whereas the fifth one is left free. So this free electron will be, that is the bond. Yes, this is the bond picture where you can see how the bonding is happening with the neighboring silica atoms, and you can see now how the free electron is there in between the vacant site. Okay, and this free electron will be very nicely roaming around, and when you give some external energy, this can pick up the external energy and assist the material to conduct. Thus the material conducts, or thus the intrinsic semiconductors like insulator properties are now being altered as conductor properties. So thus that's why semiconductors enable you to tailor its properties. Okay, so now moving ahead, if you go into the band picture, when you add the dopant, what will happen is these valence band, in the valence band, whatever the electrons are there, these are the valence electrons of the mother lattice, that is a silica lattice, and you are now adding phosphorus, and whatever the number of atoms you add as the impurities, those are donating. If you go back, what is happening now, this phosphorus is it is donating this free electron to this whole lattice. So I can call this as a donor, and this donor will now be forming a level beneath or just nearer to the conduction band. Why near the conduction band? Why? Because now this is having a free electron. Free electron will always be very active, and it can jump to the higher energy level. So I'm saying that it will be falling very nearer to the conduction band. So now what will happen as you raise the temperature? What will happen as you raise the temperature? First, there are electrons here, okay, which are filled in various energy levels. Normally it should be following the Pauli's principle, and only 2 should be there, but just for your understanding, I'm drawing like this. And now the phosphorus atoms are there here. So now as the temperature, and this is the donor energy level, normally, which you represent it as ED. So now what will happen at this particular thing is, as the temperature is raised, when T is greater than 0 Kelvin, the phosphorus atom, which is having 1 free electron, suppose if this phosphorus atom is having 1 free electron, it will give away its, if it's having 1 free electron, this 1 free electron is being donated to this. taking the energy which you give, this phosphorus atom is leaving its, or it's donating its electron, the one free electron. So that means, rather in intrinsic, what happened, when once you give an energy, the electrons in the valence band are first being excited to the conduction band. But now here, rather than the electrons in the valence band, what will happen is the donor atoms, which are the phosphorus atoms, which are having one free electron, that free electron will respond to the higher energy you give, and though that free electron will absorb the energy and rise to the conduction band. So as you know, in your previous studies, you might have seen sodium. Okay, sodium, it will be having higher ionization energy, and it will be always having 11 electrons. 1s2, 2s2, 2p6, 3s1. So one valence electron, it will be always be ready to give that one valence electron. So once this one valence electron is given off, it will gain, losing one electron, it will gain a positive charge, and because it is following the octet configuration, gaining 8 electrons in the outermost shell after losing this one electron, you can call this atom being converted into a sodium ion. Thus, the sodium has got ionized, and if you take chlorine, which has property to take the electrons to it, so it will always be ready to take this one electron which is offered by the sodium, and thus form a ionic bond between sodium and chlorine. So there chlorine is gaining one electron, hence you get Cl minus. The sodium atom and chlorine atom gets ionized. Okay, so now the same way here, phosphorus atom is also offering its one electron, and gets, once it offers one electron, it becomes phosphorus ion. Okay, so thus when you keep on raising, what will happen? Okay, this has gone, maybe later this will go. You're still raising, this will also go, and this also gets transformed, Next, what is the turn? The turn is now for the valence band to give away this and form a hole. So now if you still go on and on, there will be an electron and a hole pair formation. Okay, and there will even be, still if you go on and on, there will be even a possibility for the recombination event to happen. Whatever it is, if you observe here, the number of holes are very less when compared with the number of electrons in the conduction band. So if you see here, there is large probability for the number of electrons to be more than the number of holes. That means number of electrons in the sense negative charge, negative starting with N, hence you call this as N-type semiconductor. So when you take an intrinsic semiconductor, dope it with a pentavalent impurity, and when you raise the temperature, the number of the valence electrons in the conduction band, the number of the free electrons in the conduction band will be more. Even when you take, just when you dope it also, the one valence electron which is offered by the dopant to the lattice which is receiving it, is a free electron. So there is less possibility for the hole to happen at that particular instant. Even then also you can call it as an N-type semiconductor, because the number of the electrons are greater in number than in comparison with the holes. So thus, because of the electrons being the majority charge carriers, majority in number, you call this as an N-type semiconductor. So moving on, let us now try to derive an expression for the carrier concentration and which are the electrons and even the density of it. So for that, let me take Nd as the number of the donor atoms per unit volume of the material, and Ed is the donor energy level which is forming beneath the conduction band, very nearer to the conduction band. So as I have told you in my previous lectures which we have seen for my intrinsic concentrations and intrinsic concentrations of the electrons and the holes, that is in the intrinsic semiconductors, what did we do? First we have taken the product of the density of states and the possibility or the probability for the electrons to go and occupy that conduction band, or the possibility for the hole to be formed in the valence band when the electrons are excited to the conduction band. So the same way here also, you will have to take the number of atoms to be ND. What are these atoms? Donor atoms per unit volume. Because as many as the donor atoms, so much the donor ions will be formed. Because unless the atom is there, there will not be a possibility to be forming a ion. So it depends on the number of the donor atoms and the probability. Probability, what did I say? It is given by the f of E is equal to 1 by 1 plus exponential of E minus EF by kBt. Okay, so now here, this is the valence band, and this is the conduction band, and this is the intrinsic Fermi level, I should say. Intrinsic Fermi level in the sense what? A Fermi level which should be there between the conduction band and the valence band for an intrinsic semiconductor. But now you have doped it with a pentavalent impurity which is forming a donor level beneath the conduction band. So now after the doping is happening, the Fermi level will be here. So here E is much greater than EF. So for here now, EF is greater than ED. So what should you take now? 1 by 1 plus exponential of EF minus ED by kBt. And as EF is greater than ED, it will the exponential to the power of something here when EF is greater than ED will be always greater than 1. Hence 1 can be neglected. If you want to look why, the reason, you can go back into my previous video lectures where I have explained very clearly. So exponential of EF 1 by e to the power of x can be written as e to the power of minus x, EF minus ED by kBt. So thus you arrive at the probability as exponential of minus of EF minus ED by kBt. Now, the number of donor atoms per unit volume. If you have to have it, first you know the number of density of the electrons in the conduction band in pure semiconductors, which is already calculated in our previous lectures. In a pure semiconductor, if you take, it is 2 into 2 pi, this expression, the equation number 2. Why are you considering this? Why? Because at very low temperatures, the number of electrons in the conduction band will be equal to the number of ionized donors, right? Why? Because suppose if I am taking one phosphorus here, okay, one phosphorus atom here, because it is having one free electron, even a low temperature is enough for me. Okay, so now at an even low temperature, this will offer its one electron here. One electron, and this will now become phosphorus ion. So now this is an ion. Okay, so now if there is one electron here, there is one phosphorus ion. Next comes the turn for the next phosphorus atom. As you are continuously exciting it with the exciting energy, this phosphorus atom will donate its one electron, transforming to a positive ion. So now if there is second electron, there are two positive ions. So the number of electrons in the conduction band must be equal to the number of ionized donors, which are the phosphorus ions. So now you have, that's the reason why I have taken the number of electrons already calculated in my previous video lectures, and now I can equate it to the number of ionized donors, which I have it as the product of the probability and the number of the donor atoms per unit volume of the material. So now taking both of them and equating both of them, then you have something here, e to the power of something and e to the power of something. Bring both of them to one side and try to arrive at EF. Okay, just like we have done in our previous video lectures. So if you have to, here there is E. So if you have to get rid of E, you have to take logarithm on both sides and before carefully you do it, and after taking logger, then bring this kbt to the other side, and then you slowly send this ec plus ed to this side, and you get ef by dividing with 2 on either side, so that 2 will be cancelled here. Okay, so it's a very simple calculation till now. So now from this, what do you understand? At t is equal to 0, what will happen? This whole terms, this even at a very mild temperature also, it will become 0, and EF will be between EC and ED by 2. That means it will be in between EC and ED. That's what I have picturized in my previous slide. It is mathematically proved. Now what will happen if I still raise it to even more temperatures? Okay, so if at t is equal to 0, I have this, and now holding on to this, if I raise it to the higher energy level, the Fermi level slightly shifts upwards towards the conduction band. So let's see how. And later what will it happen? So now what will happen here is, there is a Fermi level here. This is the intrinsic Fermi level, Fermi level, which should be there for an intrinsic semiconductor. And so this is the donor. Let me draw like this. It's not given in the picture. This is the donor level, and this is the conduction band, the lower level of the conduction band, maybe EC. Okay. So now the Fermi level of this extrinsic semiconductor is this, EF. So now this Fermi level, what is it happening? As you are raising the temperature, from 0 Kelvin, at 0 Kelvin it is here. And there are phosphorus atoms here. So now as you are raising, what will happen? Temperature, as you are raising, the phosphorus atoms will become ionized. And as they are ionized, what will happen? The electrons are being excited towards the conduction band. So it will slowly try to move up towards the conduction band, and thus it will come here. And now as you still go, the number of the phosphorus atoms which you are just doping in little quantity, which will be enough for the intrinsic poor conductivity nature to go in the intrinsic semiconductor, will be all be ionized, and now it's turn for the electrons in the valence band to be shifted to the conduction band. So what will happen now, as these electrons are being shifted, this Fermi level will slowly try to come down and approach the intrinsic Fermi level. Okay, so this is what is happened. The Fermi level shifting is nothing but, what is Fermi level? The energy level which has the probability of occupancy of the electrons, right? So the probability of the occupancy of the electrons is first towards the conduction band as the phosphorus atoms are ionized. So it moved towards the conduction band a little. But as you are severely raising the temperature, what is happening now? Occupancy of the electrons is towards the valence band, because the valence band is now offering the electrons up. So what will happen? It will slowly come down. Okay, so what if you are, this is for one particular amount of the atoms, like 10 to the power of 21. Suppose if you're increasing the number of the donor, that is the impurities, the dopants, you are more and more increasing, what will it happen? What will it happen is, if the lower the number of phosphorus atoms, the fast the ionization will take place. As the phosphorus atoms are increasing in number, it will take time. It will take time for the phosphorus atoms to ionize. So, though here immediately, so here itself it has started, but here there is a lag. There is a lag, and though here at this temperature it has started coming down, but it took some more temperature for it to fall down. And though it has fallen down at the same temperature, it couldn't reach the intrinsic Fermi level as it has been reaching. It couldn't reach the Fermi level as it has been reaching for lower number of atoms. So this is how you will have to understand the Fermi level shifting with temperature and the number of the donor atoms. Okay, so now moving ahead, we are still not yet arrived with the density of the electrons. Now that you have EF, try to insert it in the density of the electrons in the conduction band, which you have already derived. Okay, so now just try to make it simplified, just solving out this minus and pushing it inside, and you have EF given as pink font. You just substitute it here. And go for simple algebra, and you will arrive at this particular form. Okay, so this is a very much easier algebra, which I cannot do it here on slide, but you can do it on your paper, which is very easy for you. Any even 10th class student can do. So I encourage all of you to do this algebraic solving, so that you will end up here. And holding on to this discussion, I want to just give a conclusion that an extrinsic semiconductor is any doped intrinsic semiconductor, either with third like pentavalent impurity or a trivalent impurity. And these pentavalent impurities or the trivalent impurities are known as dopants, and this process of adding the dopants is known as doping. And at present, we are in N-type semiconductors, we are discussing where a pentavalent impurity is taken as a dopant. And this dopant will act as a donor because it has one valence electron which is dangling in the lattice. And this dangling electron will be able to take the energy whichever you give, and it will help the intrinsic semiconductor to conduct. And this dopant, when you add, it will be forming of energy level beneath the conduction band. And when you see always the majority charge carriers will be the electrons, even as you raise the temperatures. And at 0 Kelvin, if you take, the Fermi level always lies between ED and EC. But as you raise the higher temperatures, the donors will get ionized, and the breaking of the covalent bonds also will happen, and even may lead to the electron hole pair generation. So as the temperature rises, the Fermi level moves towards the intrinsic Fermi level, and even when compared to the higher donor concentrations, there will be the lower donor concentrations will be having like slow movement. So the lower donor concentration, the fast the Fermi level will be shifting towards the lower ones. So when compared with the higher donor concentrations, will be having slow movement of the Fermi level downwards. Okay, hope you all have followed. In my next video lecture, we will be continuing this topic of the extrinsic semiconductor. We will be seeing the p-type semiconductor and looking into the same topics, whatever we are seeing, like what dopants you are adding, what will be the change of the Fermi level, what will be the concentration derivation, and what will be the shifting of the Fermi level when there is a rise in temperature. Meet you in my next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.